Do really you think you understand freezing? You've seen ice your entire life. You put it in your drinks. You've slipped on it in winter. You've watched frost crawl across your windshield. Freezing is ordinary, mundane, boring even. So you must understand it, right? Okay, explain it to me. What actually happens when water turns to ice? Not what you call it, not it gets cold or it solidifies. What happens at the level of atoms, molecules, the actual stuff that water is made of? What changes? Most people go blank. They say something vague. The molecules slow down, the water gets hard, it changes state. But those aren't explanations. Those are just different words for the same mystery. You're describing what you observe, not what's happening underneath. Here's what bothers me. You've interacted with ice thousands of times. You've made ice. You've melted ice. You've watched condensation freeze on cold glass. And yet if I asked you to tell me, really tell me, why water becomes solid at 0 degrees Celsius, you couldn't do it. You'd guess. Music, you'd wave your hands. You'd repeat something half-remembered from school about molecules slowing down, and you'd have no idea if you were right. That should disturb you. You live on a planet where water freezing and melting drives the weather, shapes the geology, makes life possible. Ice ages, ocean currents, the water cycle, clouds, rain, snow. All of it depends on this one transition. Liquid to solid, solid to liquid, and you don't actually know why it happens. The truth is, freezing is one of the strangest things in the universe. Not because it's complicated, but because it reveals something deep about how matter organizes itself. Something that breaks your everyday intuition about what solid and liquid even mean. And once you see what's really going on, once you understand what happens at the molecular level, when water freezes, you'll never look at an ice cube the same way again. But before we go any further, I need you to understand something about the question you're asking. When you ask, why does water freeze? What do you actually want? Think about it. You want me to compare freezing to something else, something you already understand. You want me to say water freezes because of X, where X is some familiar thing like dominoes falling or balls slowing down or whatever fits neatly into your existing mental model. But here's the problem. Freezing is the familiar thing. You've known about ice since before you could walk. It's one of the most basic experiences of being human. So when you ask me to explain it by comparing it to something more familiar, you're asking for something that doesn't exist. There's nothing more familiar than freezing. What you really want, and this is important, is for me to explain freezing in terms of something simpler. You want me to reduce it to components you can visualize, and that I can do. But I need to warn you, the deeper we go, the stranger it gets. Because freezing isn't just about temperature dropping. It's not just things slow down and get hard. It's about a fundamental reorganization of matter. It's about chaos turning into order. It's about molecules that were tumbling randomly, suddenly locking into precise geometric arrangements like soldiers snapping to attention. And the forces driving this, the actual physics underneath, are the same forces that hold your body together, that make chemistry possible, that allow atoms to exist at all. You're not asking a simple question. You're asking about one of the 4 fundamental forces of the universe expressing itself in your freezer. So, let's stop pretending this is ordinary. Let's stop acting like freezing is something you learned in 3rd grade and now fully understand. You don't. Nobody explained it to you properly. They gave you the cartoon version. Molecules slow down, water becomes ice. End of story. Real story is so much stranger and so much more beautiful. Now, let's talk about temperature, because everything you think you know about it is wrong. You think temperature is a thing, a property, something that water has like color or weight. You look at a thermometer and see a number, 20 degree, 50 degree, 100 degree, and you think that number represents something real, something fundamental about the substance you're measuring. It doesn't. Temperature is not a thing. Temperature is motion. That's it. When you measure temperature, you're measuring how fast molecules are moving, how violently they're vibrating, spinning, crashing into each other. A thermometer doesn't detect some magical property called heat. It detects collisions. Molecules slam into the thermometer, transfer their kinetic energy, and the thermometer translates that into a number you can read. That number is an average. an average of chaos. Right now, the water in a glass on your desk, if it's at room temperature, contains molecules moving at wildly different speeds. Some are practically crawling. Others are screaming along at hundreds of meters. Temperature is just the average kinetic energy of all that molecular madness, nothing more. So, when you cool water down, you're not adding coldness. Cold isn't a substance. You're removing energy. You're slowing the molecules down. Each molecule has less kinetic energy, moves slower, vibrates less violently. The average drops, the thermometer reads a lower number. That's all cooling is theft. You're stealing motion from molecules. And here's what that means for freezing. When water approaches 0 degrees Celsius, the molecules are moving slowly, really slowly. They still have some kinetic energy. They're not stopped, but they've lost most of their speed. They're no longer careening around like bumper cars at a carnival. They're drifting, sluggish. And that slowness changes everything, because when molecules move slowly, other forces start to matter. Forces that were always there but couldn't get a grip when everything was moving too fast. Forces that have been waiting patiently for the chaos to calm down. Forces that will grab those water molecules and lock them into place. But to understand those forces, you first need to understand what water actually is. And I promise you, it's stranger than you think. Water, 2 hydrogens, 1 oxygen. You learned this in elementary school. It sounds simple. It's not. Let's look at what that formula actually means. You have an oxygen atom at the center. Oxygen has 8 electrons. It wants 10, or rather, it wants 8 in its outer shell to be stable. It's greedy. It needs 2 more electrons to complete its outer shell. Now you have 2 hydrogen atoms. Each hydrogen has 1 electron. Each hydrogen would be more stable with 2. Music, so they make a deal. Oxygen shares electrons with both hydrogens. Each hydrogen shares its electron with oxygen. Covalent bonds form. Everyone gets closer to having a full outer shell. Stable, happy, done. Except it's not done, because oxygen doesn't just share those electrons. Oxygen hoards them. Oxygen is more electronegative than hydrogen. It pulls electrons toward itself with more force. So even though the electrons are technically shared, they spend more time near the oxygen than near the hydrogens. This creates a problem, or rather it creates something remarkable. The oxygen end of the molecule becomes slightly negative. It has more electron density. The hydrogen ends become slightly positive. They've had their electrons pulled away. The water molecule is lopsided, unbalanced. It has a positive side and a negative side. It's polar. You know what else is polar? A magnet. North and south, positive and negative. And just like magnets, these polar ends of water molecules can interact with each other. The positive hydrogen of one molecule gets attracted to the negative oxygen of another molecule. Not as strongly as a covalent bond. This is weaker, subtler, but it's there, always there. And it changes everything about how water behaves. This attraction has a name. It's called a hydrogen bond. And hydrogen bonds are the key to understanding why water freezes the way music does. So water molecules are polar, positive N, negative N. And here's where it gets interesting. Opposite charges attract. You know this from magnets, from static electricity, from rubbing a balloon on your hair. Positive pulls toward negative. It's one of the most fundamental behaviors in the universe. So what happens when you have billions of water molecules floating around? Each one with a positive end and a negative end. They reach for each other. The positive hydrogen of one molecule stretches toward the negative oxygen of another, not touching, not merging, not forming a covalent bond. This is something different, something weaker, but something absolutely crucial. This attraction is called a hydrogen bond. Music, and I need you to understand, hydrogen bonds are not like the bonds holding the water molecule together internally. Those covalent bonds are strong. It takes serious energy to break them. Hydrogen bonds are roughly 20 times weaker. They form easily. They break easily. They're delicate. But here's the thing about delicate forces acting in enormous numbers. They add up. In a single drop of water, there are roughly 1.5 sextillion molecules. That's a 1 followed by 21 zeros. And every single one of those molecules is reaching toward its neighbors, forming hydrogen bonds, breaking them, forming new ones. Trillions of tiny handshakes every second. An invisible web of attraction permeating the entire liquid. You can't see it. You can't feel it directly, but it's there. It's always there. And it's responsible for almost everything strange about water. Why water has such a high boiling point compared to similar molecules. Why water has high surface tension. Why ice floats. Why life exists. All of it comes back to this secret attraction. This constant, restless, endless reaching of positive toward negative, hydrogen toward oxygen, molecule toward molecule. Now picture liquid water at room temperature. What's happening at the molecular level? Chaos. Pure beautiful chaos. The molecules are moving fast. They have kinetic energy. They're vibrating, rotating, slamming into each other, bouncing apart. And yes, hydrogen bonds are forming constantly. A hydrogen on one molecule drifts close to an oxygen on another molecule. Attraction kicks in. A hydrogen bond forms, but the molecules don't stop moving. They're still vibrating, still getting jostled by their neighbors, still carrying kinetic energy from the heat in the environment. So that hydrogen bond you just formed, it lasts for maybe a picosecond, a trillionth of a second. Then the molecules have enough energy to rip apart, tumble away, find new partners, form new bonds, break those too. It's a dance, a furious, frantic, constantly changing dance. No molecule stays bonded to the same neighbor for long. No structure persists. Everything is in flux. If you could somehow freeze time and look at liquid water at the molecular level, you'd see a tangled mess. Molecules pointing in random directions. Some forming brief hydrogen bonds, others flying free. No pattern. No order, just motion and chaos and energy. This is what liquid means. Not wet or flows or any of the macroscopic properties you experience. Liquid means the molecules have enough energy to break whatever bonds tried to hold them in place. They're too fast, too energetic, too chaotic to lock into any structure. The hydrogen bonds are trying. They're always trying. Every molecule wants to grab its neighbors and hold on, but the thermal energy keeps ripping them apart. It's a war between attraction and motion. And in liquid water, motion is winning. But what happens when you start removing that energy? What happens when the molecules slow down? Now start removing heat. Music, put that water in your freezer. What happens? The molecules slow down. Remember, temperature is just motion. Lower the temperature, you lower the motion. The molecules that were screaming around at hundreds of meters start to calm down. They're still moving, still colliding, still forming hydrogen bonds. But now something is different. They don't have enough energy to break free as easily. A hydrogen bond forms between two molecules. In warm water, that bond would last a picosecond before kinetic energy ripped it apart. But now the molecules are moving slower. They don't have the same violent energy. That bond lasts a little longer, then a little longer still. And while that bond holds, other molecules drift close. They form their own hydrogen bonds to the same pair. Now you have 3 molecules linked together, then 4, then 10. The bonds are still breaking. This isn't ice yet, but they're lasting long enough for something remarkable to start happening. Structure begins to emerge. Brief flickers of organization in the chaos. Little clusters of molecules holding together for a few nancons before thermal motion tears them apart. But as the temperature drops further, those clusters grow larger. They last longer. The balance is shifting. In liquid water, motion was winning the war against attraction. Now attraction is gaining ground. The hydrogen bonds are getting a grip. The chaos is starting to lose. You're watching order fight its way into existence, one bond at a time. The molecules are still dancing, but the dance is slowing down. Partners are holding on longer. The frenzy is becoming a waltz. Then, at a very specific temperature, something extraordinary happens. 0 degrees Celsius, 32 degrees Fahrenheit, 273.15 Kelvin. This number isn't arbitrary. It's not something humans made up. It's a knife edge in the physics of water. And when you cross it, everything changes. At exactly this temperature, the kinetic energy of water molecules drops below a critical threshold. The hydrogen bonds stop breaking, or rather, they stop breaking faster than they form. Music. For the first time, the bonds can hold permanently. But here's what should blow your mind. The molecules don't just freeze in random positions, locked wherever they happen to be. They organize. They arrange themselves into precise geometric patterns. Each water molecule forms hydrogen bonds with exactly 4 neighbors. Not 3, not 5, 4. And those 4 neighbors arrange themselves around the central molecule in a perfect tetrahedron, a 3-dimensional shape with 4 corners like a pyramid with a triangular base. Why 4? Because of geometry. Each water molecule has 2 hydrogens that can donate to hydrogen bonds, and the oxygen has 2 lone pairs of electrons that can accept hydrogen bonds. Music, 2 plus 2 equals 4. The shape of the molecule dictates the shape of the crystal. This is inevitable given the structure of water molecules and the nature of hydrogen bonds. This tetrahedral arrangement is the lowest energy configuration. It's not random. It's not chance. It's physics finding the most stable state. And when trillions of molecules all lock into this pattern simultaneously, you get ice order emerging from chaos, structure crystallizing out of randomness, a liquid becoming a solid, not through compression, not through molecules getting closer together, but through molecules finding their positions in a vast repeating geometric lattice. That's what freezing actually is. Now, here's something that should completely break your brain. When most substances freeze, they contract. This makes intuitive sense. The molecules slow down, stop crashing around, settle into place, they pack tighter. Solid is denser than liquid. Metal, rock, wax, alcohol, freeze any of them, and they shrink. The solid sinks in the liquid. That's normal. That's what you'd expect. Water does the opposite. When water freezes, it expands. The solid is less dense than the liquid. Ice floats. You've seen this 1,000 times and never stopped to think about how absolutely insane it is. Think about what this means. The molecules in ice are farther apart than the molecules in liquid water. The rigid, locked, crystalline structure takes up more space than the chaotic, tumbling liquid. How is that possible? It's the tetrahedral geometry. In liquid water, molecules are constantly moving, constantly rearranging. They can pack relatively close together because they're not locked into any particular configuration. They slide past each other, fill in gaps, arrange themselves efficiently through pure chaos. But when ice forms, every molecule must bond to exactly 4 neighbors at specific angles. The tetrahedral structure is rigid. It can't flex or compress, and it contains holes, empty spaces in the lattice where no molecules sit. The structure is beautiful, but it's not space efficient. The result, ice is about 9% less dense than liquid water. That's why your ice cubes float. That's why pipes burst when they freeze. The expanding ice has nowhere to go. And here's why this matters more than you could possibly imagine. Lakes freeze from the top down. The ice floats on the surface, forming an insulating layer that protects the liquid water beneath. Fish survive the winter. Ecosystems persist. If ice sank like every other frozen substance, lakes would freeze solid from the bottom up. Life in fresh water would be nearly impossible. The bizarre expansion of water is one of the reasons you exist. You want to know why water forms this particular crystal structure? Why tetrahedral? Why these angles? Why this specific arrangement and not something else? It's not arbitrary. Music, it's not one possibility among many. It's inevitable. Start with the water molecule itself. The oxygen atom sits at the center with 2 hydrogen atoms bonded to it. But those hydrogens aren't on opposite sides of the oxygen making a straight line. They're at an angle, specifically 104.5 degrees. Why that angle? Quantum mechanics. The oxygen has 4 pairs of electrons in its outer shell, 2 bonding pairs shared with hydrogen, 2 lone pairs belonging only to the oxygen. These electron pairs repel each other. They want to get as far apart as possible. If you have 4 things on a sphere trying to maximize their distance from each other, they arrange themselves into a tetrahedron. That's just geometry. But the lone pairs repel slightly more than the bonding pairs. So, they push the hydrogens a little closer together. The perfect tetrahedral angle would be 109.5 degrees. The actual angle in water is 104.5 degrees, close but compressed by those pushy lone pairs. Now, when water freezes and hydrogen bonds become permanent, each molecule bonds to 4 neighbors. 2 bonds through its hydrogens, 2 bonds through its oxygen's lone pairs, 4 bonds arranged tetrahedronally. The angle of the molecule dictates the angle of the crystal. The crystal structure of ice isn't designed. Music, it's not chosen. It's the only possible outcome given the quantum mechanical properties of oxygen and hydrogen atoms. Change those properties and you change the structure. But you can't change those properties. They're fundamental, so ice has to be ice. Given the rules of the universe, water has no choice but to freeze exactly the way it does. Here's something most people never consider. When water freezes, it releases energy. Read that again. Freezing releases heat. That seems backwards, doesn't it? You put water in a freezer to make it cold. You remove heat to make ice. So how can freezing release energy? Think about what's happening at the molecular level. In liquid water, molecules are moving fast, breaking hydrogen bonds as quickly as they form. Those molecules have kinetic energy, energy of motion, but they also have potential energy, energy stored in their positions relative to each other. When a hydrogen bond forms, energy is released. The molecules move to a lower energy state. It's like a ball rolling downhill. The ball at the top of the hill has potential energy. When it rolls down, that potential energy converts to kinetic energy, then to heat when it hits the bottom. Hydrogen bonds work the same way. When 2 molecules lock together, the bond releases energy. In liquid water, this doesn't matter much because the bonds keep breaking. Energy released, energy absorbed, it all balances out in the chaos. But when water freezes, trillions of hydrogen bonds form permanently all at once. Every single bond releases a little packet of energy. All those packets add up to something significant, about 334 joules per gram of water. That's a lot. It's called the latent heat of fusion, and it's why ice in your drink keeps the drink cold for so long. The ice can't warm up until all of it is melted, and melting requires pumping all that energy back in. This is why freezing is more than just slowing down. It's a fundamental reorganization. Molecules falling into lower energy states, structure crystallizing, energy dumping out into the environment. Your freezer has to work hard to remove all that released heat, pumping it out into your kitchen just so the water can finish becoming ice. Why does water freeze at 0 degrees Celsius, not at 10 degrees Celsius, not at minus 20 degrees Celsius, exactly 0? What's special about that number? This is where we hit bedrock. The freezing point isn't arbitrary. It's not something water decided. It's a balance point, a knife edge, where 2 competing forces are exactly equal. On one side, you have kinetic energy, molecular motion, chaos, the force that breaks hydrogen bonds and keeps water liquid. On the other side, you have hydrogen bonds, attraction order, the force that wants to lock molecules into crystal structure. At temperatures above 0 degrees C, kinetic energy wins. Molecules are moving too fast for hydrogen bonds to hold. Any structure that tries to form gets immediately ripped apart by thermal motion. Water stays liquid. At temperatures below 0 degrees Celsius, hydrogen bonds win. Molecules are moving too slowly to escape. The bonds form and hold. Structure propagates. Ice grows. At exactly 0 degrees Celsius, neither side wins. The energy of molecular motion precisely equals the energy of hydrogen bond formation. Molecules are slow enough that bonds can form, but fast enough that they can still break. You get a dynamic equilibrium. Ice and water coexisting, neither gaining ground. This temperature isn't designed. It emerges. It falls directly out of the mass of oxygen atoms, the mass of hydrogen atoms, the strength of covalent bonds, the strength of hydrogen bonds, the geometry of electron orbitals. Change any of these fundamental properties and you change the freezing point. But you can't change them. They're built into the fabric of physics. So 0 degrees Celsius isn't a human convention. It's a physical constant as real and inevitable as the speed of light. Water has no choice but to freeze exactly there. So why does water freeze? You came here wanting a simple answer. Maybe you thought I'd give you a sentence or two. Molecules slow down. Water becomes ice. Done. But now you see why that was never going to satisfy you. Water freezes because molecules slow down. That's true. But it's the beginning, not the end. Water freezes because when molecules slow down, hydrogen bonds stop breaking. The positive hydrogen of one molecule finally gets to hold on to the negative oxygen of another without being ripped away by thermal chaos. Water freezes because those hydrogen bonds have geometry. The shape of the water molecule, that 104.5-degree angle, forced by quantum mechanics and electron repulsion, dictates that each molecule bonds to exactly 4 neighbors in a tetrahedral arrangement. There's no other option. The structure is inevitable. Water freezes because that tetrahedral lattice, beautiful and rigid, takes up more space than liquid water. Ice expands, ice floats. And because ice floats, life exists on this planet. Water freezes because the electromagnetic force, the same force that stops your hand from passing through a table, the same force that makes magnets repel, the same force holding every atom in your body together, expresses itself through hydrogen bonds at exactly the strength needed to lock molecules into crystals at exactly 0 degrees Celsius. Not magic, not mystery, mathematics, structure, geometry. The universe following its own rules with perfect, relentless consistency. Every ice cube you've ever held, every snowflake, every frozen lake, all of it emerges inevitably from the properties of hydrogen and oxygen atoms, properties that were fixed at the beginning of the universe. And here's what should truly astonish you. You can understand this. You can hold an ice cube in your hand and actually know what's happening at the molecular level. That's not ordinary. That's extraordinary. That's physics, not comfort, not simplicity, truth. If this changed how you see something as simple as ice, imagine what else you're missing. Right now, you're surrounded by phenomena you think you understand but don't. Light, gravity, the screen you're reading this on, your own thoughts. All of it goes deeper than you know. Subscribe to Feynman Physics and hit the bell. Every video on this channel is built to do exactly what this one did. Break your assumptions. Tear down the cartoon explanations you learned in school and rebuild your understanding from the ground up. The way physics actually works. Your subscription keeps this channel alive. It tells the algorithm that this matters. It helps me keep making these videos instead of dumbing things down for clicks. And it means more people get to see the universe the way it actually is, not simplified, not comfortable, real. Subscribe now. The next video might destroy everything you think you know. See you on the next one.